So previously we were discussing this equation where y hat equal to sigmoid transpose of w x plus b, where sigmoid of z was equal to 1 upon 1 plus e raised to minus z. So given that we had these things x1 y1, just imagine these things are in superscript x2 y2 xm ym. Where we want y hat I plus yi. To learn parameters for the model, we are given these examples, and it seems natural to get intuition to find the parameters w and b. So at least, and on the training prediction, you have on the training set, which I will write as a yi almost slightly equal to y hat I slightly equal to yi. So you got the training set y hat I slightly equal to yi. So it will be closer to the ground truth label you got as a training set. Y hat is defined at top for training example x, and of course each training example we are using the superscripts with the round braces with the parenthesis to index different training examples. So your prediction on the example 1 is I going to be y hat I, just the similar thing, similar to yi. Sigmoid function applying to that same thing will be equal to z to the I is equal to transpose of the w x will be in the front and I plus b. So in this xi refers to data via yi or zi associated to ith example. So now we are going to explore the concept of loss function. So imagine how we can tell if someone is happy or sad. Like if they are smiling, that means they are happy, but if they are frowning, that means they are sad. Well, computer can feel emotions like humans do, but they can try to guess what person might be feeling based on what they say or write. One way computers can try to guess how we are feeling is by using something called logistic regression. It's like special math formula that helps computers to figure out if someone is happy or sad based on the what they have said or written. Let's look at an example. So first of all, I'll just write what concept we are exploring. So this is loss function. This is the concept of loss function, what we are trying to understand. So Now we are going back to the example. So imagine you told your friend that I'm really happy today, and then your computer has to guess how happy you're feeling. The computer would use some numbers and special math formula called the sigmoid function to figure it out. But there is a problem. If computer guesses that you're really happy but you're actually really sad on the inside, then computers will get it wrong. And if it thinks you're super happy but you're just okay, then it will also get it wrong. So we need to find a way for the computer to know exactly how happy or sad you are. That's where the loss function comes in. The loss function is like a special test where computer takes to see if it is doing good job guessing your emotions. It is like a game where computer tries to guess your emotion and then tells we uh, then we tell if it was right or wrong. But there's another problem. If the computer is trying to guess how happy you are and it is just using one number, it might not work very well. That's why we have to use special formula called loss function, which helps computer figure out what numbers to use that it guesses your emotion correctly. So we have got the math formula called logistic regression that helps the computer guess how happy or sad you are based on what you said or written before. And we have also got the special test called loss function that helps the computer figure out of it is it doing the good job of guessing your emotion. Now let's talk about something cool. We can think of logistic regression as really tiny neural network which is like mini brain that helps computer to make decisions. It's kind of like how our own brains help us figure out what we are feeling based on what we see and experience. So now we are going to learn how those things work. So how will loss function is basically telling how well your algorithm is doing. So we are going to define loss function just like this, y hat and y. So we are going to define where the algorithm outputs y hat. The true label is square error or the one half square error. Y hat minus y squared. So you could do this, but in the logistic regression, people don't usually do this, because when you come to learn parameters, you find that optimization problem which we will go through later becomes non-convex. So you end up with the optimization problem where you have multiple local optima which will look like these. And so gradient descent may not find local optima. So whatever things I just said, if those things doesn't make sense, don't worry, it will make sense in the upcoming videos. So we'll go through the equation again. So loss function y hat y equal to half of y hat minus y square. So this means how good y hat is when true label y, and this means a squared error might seem like a reasonable choice to accept that it makes gradient descent not work really well. So in the logistic regression, we define different loss function that plays similar role as the squared error, but we will give us optimization problem which will be convex. So that will look like this, which will be different than the problem with local optima which we looked at here. So that is really nice thing. So later we are going to learn about this as well. So logistic regression is going to be y hat comma y equals to negative y log of y hat plus 1 minus y log of 1 minus y hat. So this equation is really important, so please remember this equation really well. This is L log L of y hat y, and so here if we are talking about the square error, we are going to uh, need that to be as small as possible. And with this logistic regression loss function, we will also want this to be small as possible. So we want all things as small as they possibly can. So there are two cases in this equation. So let's explore when y equals to 1. If y is going to be 1, then this term is going to be 0. So we are going to end up with y hat comma y equals to log y hat minus log y hat. So second term is going to be 0, so it doesn't mean anything. Okay, so we want log y hat to be large, as big number as possible, and y hat is sigmoid function, so it can never be bigger than 1. So y if and so that will how it will look like. So if y equals to 1, then y hat should be as big as possible. And we are going to explore the second case now, when y is equal to 0. So in this case, the function L of y hat y will look like negative of log 1 minus y hat. Cause just look at it, if we keep negative 0 in this equation, then the first term will go to 0 now, and we will be left with the minus log 1 minus y hat. So loss becomes negative. So you try to make loss function small, and now you try log 1 minus y hat large loss function, trying to make small as possible. So y hat as small as possible. So we'll discuss these things later, but we like to discuss loss function in logistic regression. So finally, loss function was defined in the term of single training example. So it measures how well are you doing in the single training example. So just keep these things in mind. I hope things are a little bit clear. It will get more clear with time. So we are going to dive in the concept of the cost function. So we are going to explore what that means in the normal things. Just so remember how we talked about the computer trying to guess your emotions. It needs to know if it is doing good job or not. That is where the cost function comes in. So cost function is like report card for computer. It tells computer how well it did last test, or how well it guessed your emotion. So imagine you're playing game where you have to guess how many candles there are, kanjis there are in jar, or candles or whatever. So computer tries to guess, and if it's right, then it is going to get a sticker. But if it is wrong, then it is going to get a minus sign. So cost function is like a score on that game. If computer guessed it correctly, then score will go up, and if it guessed incorrectly, then score will go down. So here's the thing: we want computers to guess your emotions correctly most of the time, but we set cost function to be a little bit lower for correct guesses and a lot higher for incorrect guesses. This way, the computer will try harder to guess your emotions right. So think of it like this: if you're playing a game where you have to find correct answer for and every wrong answer cost you 10 points, but every correct answer gives you 20 points. Which one would you want to do more? That's basically what cost function is doing. So it is helping computer to figure out how well it did on the last test, guessing your emotions. So uh, it can try to do better next time. So let's go back to logistic regression and how let's see how this cost function fits into all this, and let's look at the equations and formulas and how it works. So how well you do on the entire training set is what cost function is going to look on for. So we represent cost function as a j with weight and bias w and b, where 1 upon m summation of I equals to 1 to m. Now we will write loss function y n of I, and this is comma by the way, y I. So this will turn out to be negative 1 by m. I equals to 1 to m, where yi log y I plus 1 minus yi log 1 minus y hat I. So loss function is applied to single training example, and the cost function is cost of your parameters. So we'll try to find w and b in this training, in the training logistic regression model, which will minimize overall cost function j. So in logistic regression, this can be viewed as very small neural network. So in next video we will go over that, and we will develop the intuition what neural networks do and how to view logistic regression as smaller neural networks. I hope guys you will be excited for that, and I hope you guys are doing well, and as always be legendary. Peace out.